Okay, for lesson 92, we're going to be talking about uniform motion problems. And you remember you've done these before, where you have r sub f times t sub f equals r sub e times t sub e. What this really means is like rate times time. So this might be like the rate of Fred equals the rate of Ernie. And then you've done substitution before, where t of f is equal to 16, t sub e is equal to 12, r sub e is equal to r sub f plus 15. So you just substitute in and then solve. So let's see, r sub f is not equal to anything, so that'll stay like that. T sub f is 16, so we substitute that in. R sub e is this, and then that's being multiplied by t sub e, which is 12. And then this, I'm just going to flip that around because I like the coefficient in front of the variable. So 16 r sub f, we're going to distribute here. So we get 12 r sub f is equal to 15 times 12. So that's equal to, plus 180. And then solving for equations, constants on one side, variables on the other. So I'm going to move this variable over here. Because it's being added, use the inverse operation and subtract. So we have r, 4r sub f is equal to 180. And we divide both sides by 4. And then we get 4 goes into 18 4 times. There's 2 left over. 4 goes into 20, 45. So then we had solved for that. So you've done those already. Now we're going to take that whole idea and use it to solve for uniform motion problems. And with these uniform motion problems, distance 1 for something is always going to equal distance 2. So our main equation is going to be this. Distance 1 is equal to distance 2. And that could be a problem such as somebody starts off and they're riding their bike and they go a certain distance and then their bike breaks down and they have to walk back home. And that distance that they cover is exactly the same. Or it could be two people start off and they cover the same distance. In this case, this would be distance 1, this is distance 2, same thing here. But you can see from these diagrams that distance 1 is equal to distance 2 in both of these. And then the key thing that we're going to do is we're going to change distance, because if you remember, distance is equal to rate times time. So instead of writing d1, we're going to do rate 1 time 1, so rate times time, which is the same thing as distance 1, is equal to rate 2 times time 2. Okay, so this is going to be your main equation. You're going to turn this main equation into this because distance is equal to rate times time. All right, let's take a look at some examples now. So we'll look at example 92.1. It says, on Tuesday, the express train made the trip in 12 hours. On Wednesday, the freight train made the same trip in 16 hours. Find the rate of each train if the rate of the freight train was 15 kilometers per hour less than the rate of the express train. So the diagram that we'd be looking at, we see from the problem that they both made the same trip. So this is what's this? This will be the express train, and then the freight train made the exact same trip. So this is the distance of the express, the distance of the freight. They're equal to each other. So we could say distance E is equal to distance F. Well, we're going to change this to rate of the express, time of the express, is equal to rate of the freight, time of the freight. Now let's check some more information and try and figure out all of these other variables here. So, it says here on Tuesday the express train made the trip in 12 hours. So the time of the express is 12. On Wednesday the freight train made the same trip in 16 hours. So the time of the freight is 16. So we have 2 of them. We need at least one more. The rate of each train, find the rate of each train. If the rate of the freight train, so I'm gonna, where am I gonna write this? The rate of the freight train was 15 kilometers less than the rate of the express. So 15 kilometers less, the rate of the express, 15 kilometers less. So we know that the rate of this one is slower than this one. So this number is smaller. So if we take this and take 15 away from it, that's going to give us a smaller number. So I think we have this set up correctly. And now we're just going to plug all of this in. So we have solved for our f. So we're going to solve for RE. That'll be our variable. TE was equal to 12. Our F is equal to RE minus 15. TF is equal to 16. I'm going to put my coefficient in front. We're going to distribute. So we get 16 RE minus 16 times 15. Minus 240. Variables on one side, constants on the other. So we're going to subtract 16 RE from both sides. We get negative 4 RE is equal to negative 240. Divide both sides by negative 4. The rate of the express is equal to 60. If the rate of the express is equal to 60, we plug it in here. The rate of the freight then is 60 minus 15, which is 45. So that is example 92.1. But if you notice, start off with this main equation, set the distances equal to each other, change distance to rate times time for both of them, come up with your equations and plug them in just like you've been doing. All right, let's look at 92.2. It says the members of the girls club hiked to Lake Tenkiller at 2 miles per hour. Mr. Alley gave them a ride back home at 12 miles per hour. Find their hiking time. So find their hiking time if it was 5 hours longer than their riding time, and how far was it to Lake Tenkiller. So if we notice with this one here, they hiked this way and they rode back this way. So this was hiking, this was riding. The rate of hiking was 2 miles per hour. He gave him a ride back. The rate of riding was equal to 12 miles per hour. Remembering our main equation, the distances are equal to each other. Going to change distance to rate times time. Distance is equal to rate times time. We know that this is 2. We know that this is 12. And now we're going to read the rest of it to solve for one of these two. It says find their hiking time. Find their hiking time if it was 5 hours longer than their riding time. So let's do that. So time hiking, I'm going to set it equal to time riding. And we know that this was longer. So this is a bigger number. So to add the 5, we're going to add the 5 over here so that this would become equal. And then we're going to just substitute. For TH, it's solved for this, so we're going to put this in here. And then this is going to be our variable. It's just that. Distribute again. So we get 2TR plus 10 is equal to 12TR. Variables on one side, constants on the other. We get 10 equals 10TR, so the time writing is equal to 1. Well, if the time writing is equal to 1, then the time hiking is equal to 6. That's example 92.2. Okay, one more. And then I'll let you try the practice. 92.3, Durant drove to the oasis in 2 hours, and Medill walked to the oasis in 10 hours. How far is it to the oasis if Durant drove 16 miles per hour faster than Medill walked? Okay, so here we go. So again, with our drawing, Durant drove, so this is Durant driving. This is Medill walking. The rate of Durant was, time. Let's see. Okay, we know time of Durant. Durant was 2 hours. We know the time of Madrid was 10 hours. And then as far as the rates, what we're going to do with these, okay, we're going to start off setting them equal to each other. We're going to read the sentence and decide which side we need to add to. Okay, how far is it to the oasis if Durant drove 16 miles per hour faster than Medill? All right, so he was faster. This is going to be the bigger number. So we're going to have to add the 16 to this one so that they'll be equal to each other. Okay, our main equation, distance of Durant equals distance of Madrid. You don't have to write this each time if you understand that rate times time is equal to distance. Okay, and we're just going to plug stuff in. RD is equal to RM plus 16. TD is equal to 2. RM, that's the variable we're going to solve for. TM is 10. Okay, we're going to distribute 2RM plus 32 is equal to 10 RM. Constants to one side, variables to the other. So 32 is equal to 8 RM. Solve for the variable by dividing each side by 8. Rate of Medill would be 4. If the rate of Medill is 4, the rate of Durant then will be 4 plus 16, which is 20. Okay, let's see what the question had. Okay, so now we read the problem to get the time and the rate equations. Distance, okay, and if they were looking for the distance would be, so how far is it? So they're looking for distance. So remember that distance is equal to rate times time. We can do either one of them. We could do the time of Medill times the rate of Medill. So that would be 4 times 10. So the distance would be 40. Or we could do the rate of Durant and time of Durant, which would be 20 times 2, which would also be 40. So they're both going to be the same. Okay, go ahead and pause the video, work through the practice, and then come back and see how you did. Okay, practice A. Candide and Pangloss walked to the site of the disaster in 9 hours. The next morning they jogged back home in 3 hours. So let's see. They walked, then they jogged. Walked, jogged. So we know the time of walking. They said they walked there in 9 hours. The next morning they jogged back. Time of jogging was 3 hours. How far did they jog? So again, we're going to be looking for the distance at the end. How far did they jog? If they jogged 4 miles per hour faster than they walked. So we're going to set those up. Rate of jogging, rate of walking. Which one was faster? Jogging faster. So we're going to add the 4 to the walking so that these would be equal to each other. Again, distances are equal because you see they travel the same distance. So rate times time equals rate times time. This rate is what we're going to solve for. This time is 9. This rate, we're going to substitute this in. This time is 3. So I'm going to move the coefficient in front. I'm going to distribute. Variables to one side, constants to the other. So 6RW is equal to 12. So RW is equal to 2. Well, if RW is equal to 2, RJ is going to be equal to 6. To find the distance, we can do either rate times time. So let's do RJ, or the jogging. So